a beautiful blue marble. Who would guess that serious changes are taking place in its atmosphere? These visible wavelengths are only a part of the electromagnetic spectrum. What you don't see are the radio, infrared, gamma, X-rays, and the sun's harmful ultraviolet rays, known as UV. So how does ozone play a part in this story? Ozone is a relatively unstable molecule found in the 3 layers of the Earth's atmosphere. In the stratosphere, ozone acts like a warrior's shield, protecting us from the sun's ultraviolet radiation. With the depletion of ozone, we become more vulnerable to skin cancer and cataracts.
Ozone is O3. In other words, the ozone molecule is made up of 3 oxygen atoms. Ordinary oxygen is O2. High-energy ultraviolet radiation in the stratosphere breaks oxygen molecules apart, forming 2 separate oxygen atoms. These oxygen atoms are highly reactive, and they quickly join nearby oxygen molecules to form ozone. Stratospheric ozone protects us because it efficiently absorbs ultraviolet radiation. The absorbed UV energy splits ozone into an oxygen atom and an oxygen molecule. The free oxygen atom quickly combines with a nearby oxygen molecule to reform ozone. We see that ozone forms, breaks up, and forms again in a repeating process. Because of this continuous repeating process, UV is absorbed by ozone and less reaches Earth. Because ozone is a highly reactive molecule, it interacts readily with nitrogen, hydrogen, bromine, and chlorine compounds. For example, when a chlorine atom collides with an ozone molecule, it steals an oxygen atom to form chlorine monoxide, and it leaves behind an ordinary oxygen molecule. When a free atom of oxygen collides with the chlorine monoxide, the 2 oxygen atoms bond to form an oxygen molecule. The chlorine atom is thus released and is free again, free to destroy another ozone molecule. This ozone loss sequence is called a catalytic cycle and is a natural process that has always existed in the stratosphere. As a result, 1 chlorine atom may destroy hundreds of thousands of ozone molecules before it forms one of other chlorine compounds and exits the stratosphere.
The level of ozone in the stratosphere is balanced between the production of ozone due to the highly energetic UV radiation and the loss of ozone by catalytic processes. This delicate balance has been upset by a 5-fold increase of chlorine in the stratosphere since the early 1970s, causing the balance to shift to lower ozone levels. The chlorine increase has resulted from the chlorofluorocarbons, or CFCs, released in large amounts due to human industrial activity. Unlike ozone, CFCs do not break down easily. They are not water-soluble like most chlorine-containing compounds, which may be washed out of the atmosphere by rain. In fact, CFCs eventually are transported intact into the stratosphere, where their concentrations have been measured by NASA instruments.
In the upper stratosphere, the CFCs are broken apart by UV radiation, the first step in a chemical process that destroys ozone. The chlorine atoms are then freed from the CFC, and they can catalytically destroy ozone. Ozone depletion is occurring because the CFCs and other manufactured compounds are causing additional ozone destruction.
Originally, the ozone depletion process was based on theories. However, British scientists studying Antarctic ozone and NASA scientists gathering data from an ozone monitoring instrument in space were stunned in 1985 when they discovered that ozone had decreased dramatically over an area near the South Pole. We called this ozone decline and loss the ozone hole. Ozone depletion has occurred in both hemispheres of the world. Many countries contributed to the problem. Fortunately, most industrial nations have signed agreements to phase out many of the damaging chemicals. Meanwhile, the thinning of our protective ozone layer is a reality, and it adds to the basic danger of excessive exposure to the sun.